So in the last video, we looked at the different types of mirrors and what kind of images they usually form. Well, now we're going to look at the mathematical description of these mirrors. So we have what's called the mirror equation, and this relates the distance between an object and the mirror, S, the distance from the image to the mirror, S prime, and the focal length of the mirror. And the focal length is always half of the mirror's radius. And so another case of this equation is when in a plane mirror, which remember is just a flat mirror. In that case, if we set the focal length to infinity, we get that S is going to be equal to negative S prime. And this agrees with the fact earlier that the image, the virtual image in a plane mirror, is always the same distance that the actual object is from the mirror. So there are a couple of sign conventions, to use with the mirror equation. So the focal length is positive for a concave mirror and negative for a convex mirror. And S prime, the distance from the image to the mirror, is positive for a real image and negative for a virtual image. Another way to think about these sign conventions is if either the focal point or the image is on the same side of the mirror as the outgoing light, then it's positive, and if it's on the opposite side from the outgoing light, then it's negative. Now, for example, in a convex mirror, the image is virtual, so the image is behind the mirror, while the outgoing light is in front of the mirror. So then S prime is negative. So now let's look at a quick example. So you have an object 0.6 meters from a convex mirror with a radius of 0.5 meters. So from the radius, we know that the focal length is half of the radius, so the focal length is going to be 0.25 meters. And it's a convex mirror, which means the focal point is going to be on the opposite side of the outgoing light. Since the outgoing light is going to be in front of the mirror, and the focal point is behind the mirror, the focal length is negative 0.25. So then we just plug stuff into the mirror equation. S is 0.6 and F is negative 0.25, and we can solve for S prime, which is negative 0.18 meters. So since this is negative, we know it's a virtual image, and so it's a virtual image 0.18 meters behind the mirror. Now, another thing we want to look at is how big the image is compared to the original object. And so that's given by the linear or lateral magnification. So the linear magnification is the ratio of the image height, h prime, to the actual height of the object, h. And so for a plane mirror or a spherical mirror, the magnification is also going to be equal to negative S prime over S. Now, obviously in a plane mirror, S and S prime are the same, so the magnification is going to be 1, which we already said in a plane mirror, the object and image are the same height. So for sign conventions, a height is positive for an upright image and negative for an inverted image. So another quick example, we have an object which is 0.3 centimeters tall, 0.08 meters from this concave mirror. So notice how this image is in front of the focal point. So in this case, the concave mirror actually does not form a real image. Okay, so the radius of the mirror is 0.32 meters, and so focal length is half of that, 0.16 meters. And the focal length is positive since the focal point is going to be on the same side of the mirror as the outgoing light. So plugging stuff into the mirror equation, we solve for S prime, which is negative 0.16 meters. So again, in this case, when the image is in front of the focal point in a concave mirror, the image is going to be a virtual image behind the mirror. And then we can solve for the magnification, which is just negative s prime over s, which is 2. So then the image height is the object height times 2, or 0.6 centimeters. So the image is upright, twice as large, and virtual behind the mirror. Now, of course, you don't have to memorize all these different cases, like for a concave mirror, if the object is in front of the focal point, then it's going to be a virtual image, and so on. So what you do, if you didn't know, is you could draw a ray diagram. So remember the easy rays for a concave mirror. One ray is parallel, then it reflects back through the focal point, and then if a ray hits the vertex, it's reflected back at the same angle that it hits the vertex at. And then the last one we can draw is one that reflects through the center of curvature, along the radius. We can't draw the fourth one, which is through the focal point, because obviously the object is already in front of the focal point. And so if you drew all those rays, and you extended their lines back behind the mirror, then they would appear to diverge from this point. So all you have to do is draw those easy rays for a diagram.